So, ladies and gentlemen, dear colleagues, welcome. I'm Zdeněk Hanzálek, and thank you for watching the 24th installment of the scheduling seminar. Today, I'm pleased to introduce Iiro Harjunkoski. Iiro finished his PhD in '97 at Abo Academy University in Finland. And then he went for 2 years for postdoc to Carnegie Mellon University in US. He did his postdoc with Professor Ignacio Grossman. And then he started his long career in ABB Corporate Research Germany, working on different optimization and scheduling problems for various industry sectors. In 2016, he restarted his academic career as adjunct professor in process system engineering at Aalto University in Finland. And if I understood well, ABB research unit when he works was bought by Hitachi. So since 2019, he is with Hitachi as a research fellow focusing on the modeling and solutions of energy-related optimization problems. Even though he is in industry, he is very active in publishing, taking part at scientific committees of different conferences, and he has about 150 scientific journals, which is, I think, quite exceptional for somebody working in industry. So that's good for our community because it shows that scheduling is really well applied theory. And now let me ask Iiro to start his talk. So Iiro, please go ahead.
Thank you, Zdeněk. Also, a warm thanks for Zdeněk and Przemek for the invitation to be able to give this seminar today with you. And today I'm going to talk about something that is very close to my, I would say, heart also. It's scheduling and energy. So this is topics that I've been more or less working on more than 20 years, 25 years. At the same breath, I want to also acknowledge my PhD advisor, Tapio Westerlund, from Åbo Academy, who brought me to the world of optimization and always inspired me to try out to solve more difficult problems, as well as Professor Ignacio Grossman to also bring me really into this scheduling business and getting more network by working with him. So today we are going to talk about industrial challenges and opportunities related to scheduling. And one of the driving forces in this work that I'm doing is, you can see in this picture, it's electricity demand is increasing significantly in the next decades. And that's, of course, due to increasing electrification of practically anything. And this also requires much more bidirectional flows, as you can see here in the picture, to balance the power grid, and much more intelligence between all these players. You can see the number of players becomes huge. And we need more intelligence that is today in place. So optimization and schedulings are really some kind of cornerstones in this evolution. So I will not present my company, but this is a slide that they provided that fits very well as a motivational slide on my talk. It's talk about how the energy system of 2050 will look like. One claim that we believe in is that electricity will be the backbone of the entire energy system. And this we can see, for instance, already in the going away from fossil based to renewable power generation. We also see electrification, for instance, electric cars, electric vehicles, and even many industries are moving towards using more strongly electricity. And also there are some energy carriers, hydrogen, ammonia, that we have heard. That's also going to be a complementary carrier to direct electrification. So this means in practice that it should improve the energy efficiency, and basically all the markets are converting towards electrification, which means added complexity and much more opportunities also for optimization in this phase. So the goal of my talk will be basically to, first of all, highlight the importance of energy and electricity in this business, but also give some insights of solving industrial scale scheduling problems, at least trying to solve them. So I'm going to focus on demand side management, which combines process scheduling with energy and electricity scheduling. And I'm going to present some strategies how to speed up large-scale optimization problems that are typically seen there. And then I want to share some of my personal experiences from the work I have done in the melt shop scheduling and unit commitment, solving unit commitment problem. And one of the maybe things is that my own belief is that MILP is a really important component in solving industrial scheduling problems. It's not alone sufficient, but it is one of the main topics. So the outline of my talk will be as follows. I will first discuss why MILP. Then I will give a very short introduction on demand side management. And then we jump into the first problem, which is steel plant scheduling problem, which is a continuous time formulation. And then we talk about the unit commitment problem, which is a discrete time formulation. And then I conclude. So let's look at the why MIP. For instance, in this seminar series, or if you read scientific papers, we see a lot of different and excellent scheduling algorithms that could be efficiently applied to many problems. There are various policy methods, graph-based methods, TSP-based methods, constraint programming, genetic algorithms, different heuristics, approximation algorithms, and AI-based methods, and so on. So it's of course natural to question, why would we choose something like MILP, which is NP hard? However, I'm actually in a very good position because Christian Artigues gave 1 month ago, he gave an excellent speech about MILP and scheduling. So I would say he gave truly a very systematic overview with also some analytical approaches. So I'm not going to focus that much on analyzing the problems. I'm just trying to be the solver, the engineer that tries to solve tricky problems. So another thing is why MILP is that when you look at automation systems in industries, the scheduling is only one part of it. So you have the scheduling in this big chain of decision taking, and there's a lot of these are actually using optimization. And in industrial automation systems, we also have to be compatible with different layers. So we have to create compatibility at least between the neighboring sections. And in this way, I would say mathematical programming is a very good way of systematizing this task of coordination. Another way is here to see is you can say that MILP models are flexible and elastic. What I mean by that flexible, I mean that you can consider physical and business constraints that can be very, very different. Of course, they have to be linear if you want to use MILP, but most of them can be linearized and at least approximated sufficiently well. And then you don't need to adapt the model. If you have an old model that is well formulated and you add new constraints, you can actually add it, and this flexibility or elasticity comes from that part. Another thing that is needless to say, if you use commercial MILP solvers, you really benefit from top achievement from operations research and the best algorithms available. And the other one thing is, of course, with commercial solvers that you can actually also rely on them, and you can put some part of, as an industrial solution, you can put part of the reliability and liability also on the ones who provide the solvers. So then another thing from the industrial point of view is to say that you can also separate the modeling expert and the software development from each other. So you can really have people who know the process, who focus on the modeling, and other people who are then doing software development, doing the programming, trying to do interfaces and graphical user interfaces and these kind of things. And of course, as you see in the picture, scheduling is only one part of a big automation system. So that's another topic here. However, in this talk, I will put on my engineering hat. I will show some cases where a concrete industrial problem is turned into math models. And my focus will not go too much how you really go into solving this. I will talk a bit about the formulation, and then I will also talk about how we go about when we have a very large scale problems. So with this, let me move to the first topic that a bit sets the stage for the industrial case, demand-side management. I will give you a very short introduction. This is a topic I have been working myself since 2008, more or less. So it's 15 years anniversary soon. And this is basically a consequence of energy supply becoming much more limited and variable once you have more renewable energy sources. And this also means that when you increase the renewable generation, the prices of electricity become more volatile. So you have this market liberalization that has also created a very volatile market. And that means if you can handle it, large industrial consumers may really benefit from utilizing the flexibility they might have in their energy demand. Also, apart from having the consumption uncertainties, this renewables also create certain uncertainty on the supply of energy. So this is something where demand-side management can offer benefit in this new market environment. And it can also support the power grid. So looking a bit at this side, so demand-side management, it can be, first of all, it can be to allowing the grid operator directly control part of the electricity load in your plant. It's called ancillary services. And I know, for instance, that Alcoa and Midwest system operator in the US have been having this already. Or then the other way is that you in advance try to plan your production and schedule your production such that you avoid these electricity peaks that you can see in the image on the left. And the idea is to then consume during cheaper periods. And I'm going to focus on more this scenario in this talk. So if you look at a process, take any process here that consumes a lot of energy. So this kind of energy intensive processes, first of all, they have to buy their electricity from somewhere. And typically it's been multiple contracts. You have had earlier, there was always this kind of base load contract that was maybe done for 1 year. And then you had this time of use contracts that were maybe like night tariffs and day tariffs and so on, weekend tariffs. But these are more or less getting less and less. And this market liberalization has caused that this kind of day ahead markets where you have huge fluctuations will take over main electricity purchasing. So what somebody has to do, you have to create your schedule. And then you have to guess what will the price be for the next 24 hours. And then you have to basically provide your electricity need and make bids on this to say, I will need this much of energy during the next 24 hours. So let's try to purchase it in the best way. And once you get it confirmed, you basically have also a commitment, which is then a committed load. And if you deviate from it, you have to pay penalties. There's also on-site generation. And this is some plants also have it, not everybody, which have its own constraints that you have to take into account. And if you have too much energy, for instance, you deviate from your plan in a negative way, it may be that you even can sell it back to the grid. But this gets a bit more tricky. So what I'm going to focus on no more is this upper part here. And I'm going to talk about the steel production scheduling. As I said, it's a continuous time approach that we will take here. And let's start by looking at the entire supply chain for the steel production. So this is an image from ABB, where you can see the whole supply chain starting from the melt shop to the products and then becoming back to the scrap yard. So basically the focus in this talk will be in this melt shop, where basically we melt scrap and we melt ore, iron ore, and produce steel, which we then cast in a continuous casting unit, which is then further refined to different products. So in this part, this is a few, one picture on the process, a bit more in detail. The first step is to smelt or to melt this scrap that you get. It's done in an electric arc furnace, and this is a huge consumer. Typically, it can consume between, I would say, 70 to 150 megawatts. So it's a huge electricity consumer, and that is the largest one also in this kind of steel plants that have it. And this is done then in batches. So you fill it in with scrap a couple of times, and then you run the electrodes there to melt the scrap. And once you are done, you have a full set, maybe 100 tons or more of this melt scrap or molten metal, which you then hand over to the next step, which is the argon oxygen decarburization unit. We basically blow in a mixture of argon and oxygen to get rid of the carbon dioxide, and then it produces steel. And the third phase, the batch goes over to here to the ladle furnace. And in the ladle furnace step, you typically add some chemistry, some chemicals to create a certain steel grade. It can be chromium, for instance. And then you also adjust the temperature so that the temperature should be perfect for the next step, which is a critical step because it's a continuous casting. So in this continuous casting, it's called continuous because it should cast multiple heats or batches. Heats, they are called heats in the steel world, without interruption. That means that when my previous batch is slowly emptying, you should already have the next batch and pour it into this tun dish so that the continuous caster never goes dry, because else you have to do a lot of maintenance. So this is kind of a picture of the process, and it's an electricity intensive process with many, many constraints. And here, for instance, one constraint is you should avoid intermediate cooling. So if a heat stays too long between these stations, it can cool down, which can cause crystallizations and quality problems. You also have a lot of sequence dependencies in these changeovers. You have grading compatibility. Some grades are not simply you cannot put into the same continuous casting sequence. And you have a lot of also transfer times between equipment that depend a lot on your layout and your assignments of equipment. And then you have this normal coordination of production step as in any scheduling problem. So how do we solve this problem? It's quite complex. So this was actually something I did with Professor Grossman already in 2000 when I did my postdoc. So we basically made this algorithm where you have a different grades, steel grades. And here you can see a color represents a grade, and this kind of dashes is a subgrade, which means it has some same characteristics, but it can be cast together, but there should be some rules in which order sequence you do it. Also, you can see different widths of these boxes, and it means that you also are aiming to cast different slabs of different types, and there the geometry also plays a role. So the first step is simply sorting. First, take them out and sort them such that you have potentially compatible grades together, and these grades from one of these groups could form a potential casting sequence. Then you actually solve a problem, first MILP problem from this one. What you do is you take each of these groups and then you solve an MILP problem where you try to minimize the number of casting sequences so that you add all of these into a casting sequence, and you try to minimize the number of that you need to process all of these. And there's also an upper limit for how many heats you can or batches you can do in a sequence, which varies between 3 and 8, typically depending on the steel grade. And then after this, once you have formulated the one first MILP problem formulates a sequence, then you basically do the standard scheduling, the continuous time scheduling formulation already with fixed sequencing. And here you can see that the continuous casting is respected in this schedule, and all the other ones are then aligned such that you always have the next heat ready here by the time when this earlier heat have been cast. And the ladle furnace here actually also acts as a buffer to keep it warm for some time. So what you do then, you get this kind of partial schedules, and you get a lot of them. Typically, you may have for a week 80 to 100 heats. So you get a lot of these schedules done. And then you basically need to think, how do you put these together? So you have another MILP problem, which is then trying to figure out what is the perfect order of these. We used a kind of a slot-based approach using an MILP approach here. And then finally, once you define it, you can then solve an LP relaxation to kind of get the air out to make it a bit more tight. Or you can also use MILP to possibly change some assignments to get a more tight schedule. So what this results in is something like this. You have a schedule here, you have a 1-day schedule with 20 heats. And you can also see this is then with the example that we used also in the industry. where we have parallel equipment on both sides. And then we have basically here 4 continuous casting sequences, and this meets all these requirements that we have had here. But if I now take a look at the electricity load, how much electricity I need for my process at each time of the day, you can see that this is a load. And now, of course, the pricing is another issue that we didn't think about. So if I would take this load and I would have something like this kind of forecasted day ahead market price, it's not so good, because basically I am fully producing at the peak prices and I have this low price I'm not able to utilize. Here I have to say that this example is somewhat artificial, because of course the steel plant normally is 24-hour operations, so it would already continue with other heats here, but this is just to make it a bit more visual, that you can see the actual problem we are solving. So it's an opportunity. If you can actually take into account this electricity price, that should give you a good opportunity. And since this is a continuous time problem, we decided actually to use a global general precedence as a starting point. This is a scheduling MILP formulation by Mendes and Cerda from 2003. And basically what they do is they have a separated continuous separated sequencing variables Y. And this is global, applies for all the instances of batch I and I prime. So if this is one, I always produce batch I before I prime. And then you have a separated assignment variable, which tells me in which unit J my batch I should be processed at stage S. And that's why we have the stage S, just for generality, because in some cases the unit may be used in multiple stages. And then you have 2 continuous variables. One is the starting of a batch on a stage, and the second is the finish time of the batch of a stage. So this is a quite general approach. And I just show the main 4 main equations. This is the assignment constraint that just allocates each batch to a unit for each stage. Then you have the processing time, and here you can see that you have a start time is equal to finishing time is equal to start time, plus then duration that depends on the assignment of the equipment. This could also be a variable, and that was also one criteria here, because we, in the steel example, we needed to also be able to handle a variable processing time for some unit, for instance, a ladle furnace, to make sure that we can keep it longer there if it has to wait for the casting. Then we have sequencing variables. This is sequencing constraints, where you have then the starting time. If I comes before I prime, we say that the starting time of I prime is after finishing time of I, plus the cleaning and the setup times. And of course, since we are now talking about the scheduling, we have to add this kind of big M constraints, or use another way to formulate it. So first of all, we relax it if the sequencing variable is true, it's active, but also if the 2 I and I prime are not assigned to the same equipment, it doesn't make sense to make this constraint active. And then the same way, the other way around, if I prime comes before I, we have the same constraint, just another way around. And finally, we have a transfer time considered between the stages. So the stage precedence, we have to say that the previous stage has to finish, plus a certain transfer time before the next stage can begin. And then we basically also see this transfer time can heavily also depend on the unit selection, which unit assignment you have selected. So that's basically just a simplified plain formulation. And one of the part is now, how do we get this energy awareness put into the formulation? There are alternative formulations, but somehow you have to be able to account for the electricity consumption. So our model basically becomes, the math model becomes that as production scheduling constraints. Then we have to have some energy awareness constraints, which I will discuss here. Then you also may have price response. You have to be able to, also in the objective function, be able to understand the penalties for the pricing and deviations from committed loads. So the image here is actually showing you a task, a production task in this Gantt chart. And then you have the green dashes, so how much time do you spend within a time slot? And here, since my schedule is done in continuous time, the electricity is always sold in time slots. So it can be hourly or 30-minute slots. So that means we have time slot 1. Here's an electricity price for this time slot. And then we have a time slot 2. We have a different price, E2 here. And time slot 3 has a a different price. So now we have to actually understand how do we track this consumption, and the paper by Nolde and Morarin from 2010 actually had this very good idea of trying to track it using, I think they used 4 or 6 binary variables. So you basically can look at this as so you can basically calculate if I, for instance, start and finish my task within a time slot, then the consumption within a time slot is equal to the duration of the task, and so on. I will not have time to go through all of this, but how we then combine these time slots, we need some kind of event binaries. So what we did, we actually defined 2 binary variables, which basically just says, is my batch starting or finishing in a given time slot? And with this approach, you can see the different approaches here in the picture. And with this one, we can then basically track where how our processing times are matching with the electricity pricing over the course of the time. Then, of course, we also need to have constraints where we link this kind of process constraints. This is a start time of a stage in the process in the previous scheduling model. And then you have the start and end time of your electricity slots. So this is basically just a simplified version, and more details you can find in the publication of Hadera and al. From 2015. So this is basically the way how we could formulate the problem. And of course, I realized that there's probably a lot of could make much more tight, for instance, using some convex hull reformulations. But already this one turned out to be working. So in this case, you can see some results. So we took, we have a 20 heats and 16 heats in these different scenarios. Here we have high prices, here we have low prices, and we try to see, we get 4,000, 3,000 binary variables, and this is what you get. You basically can see that there's an integer gap, which is about 20% after 10 minutes of scheduling time, and even after 1 hour scheduling time, we couldn't reach even close to 0 gap. However, you can see that the solution is not close to optimal, but at least we cannot prove the optimality, even if it would be the optimal solution, and this still remains a challenge. However, one of the main targets of this study was also to prove that there exists, or if there exists, such a flexibility in this process that could be used for demand-side management. And here you can see in the middle of this Gantt chart, you have an electricity price. Red is expensive, green is cheaper. So you can see that compared to the original make-span-driven schedule up here, in the electricity cost-driven schedule, you can see that we avoid using this highest intensive cost times when for our electric arc furnaces, which are the biggest consumers. And we could actually see that collaborative models could actually save 5% at a pilot plant. So you can see it's not perfect. We also tried different approaches. We also looked into the resource task network approach. We looked at both at the continuous time and discrete time approaches, but as the changeovers here play a really big role, this was a bit difficult because that needs additional tasks, as well as equipment selection also affects the duration and the transportation distances. So that was one thing that spoke against the discrete time model. And in practice, when we talk to the steel plant, they need to have maximum 5-minute time granulation. So we have to have at least 5-minute exactness, which would make a discrete time approach very, very big. So what it means that even we could prove that the continuous time model actually was more efficient, it wasn't that practical. So it could solve certain problems, but in this case, it was not so good for this problem. However, some continuous problems, we could show that there were a lot of benefits of using this RTN approach. So then we also tried more. What else could we do? This was not yet sufficient. We could see clear trade-off between the two partly contradictory goals of minimizing energy cost, minimizing the make span. So we thought of, could you actually make some kind of industrial demand side managed module? So we tried some bi-level heuristics that tries to balance between the two targets. We also developed some mean value cross decomposition approaches that uses Benders and Danzig-Wolff decomposition approaches. Here you have the papers down here. And we also then looked into some game theory to try to find some good solution fast. For instance, try to coordinate these using some Stackelberg games and even multi-parametric programming by Pistikopoulos and al. But this didn't really solve, but what we could actually get, we could find nice solutions. We could see that you can actually reduce energy costs significantly by this type of approaches. You can increase your flexibility and agility of your complex processes. And we could prove that you actually can reach a 3 to 20% energy cost savings. But still the solution time was somewhat an issue. So this is one story of hitting our head together with industrial demand side management in steel. And now I would like to change a bit the tone, because here what we do, why do we do demand side management in the first place? These all eventually come together because power grids has to deal with balancing the energy demand and supply every second of the day. And demand side management again creates an opportunity of even seeing them from the grid point of view as a virtual power plant. That means if you reduce your consumption, you release energy or reduce your energy request, which can be seen as a virtual power plant. And that means that you can also look at the process on the right-hand side as a prosumer, producer and consumer. So coordination of this energy production and energy consumption is a very, very large scheduling problem. And I believe this collaboration is something that should be brought closer together. However, these are completely two different worlds. We cannot see the details of each other. So on the one hand, you have all these process related important things that could ruin your production. On the other hand, you have something, the grid is huge. It can be a countrywide grid, and you may have issues in a completely different region that is depending on your actions taken in one place. So I made this simple picture just to highlight this picture. Here we have our steel plant only alone to try to show how these things are related together. So in a traditional power system, our steel plant was there, and there were power grid made, maybe a couple of lines coming into the grid. And then you had big power plants that would then produce sufficiently energy needed by the plant. And also these grids were dimensioned such that they can handle it together. And today, the modern power system has a lot of different concerns because big power plants are replaced by these smaller renewables. So you will have a lot more distributed energy generation. It's also not always at hand. So the TSO, or the transmission system operator, has to now really concern. His concern is not only electricity availability, but also the network capacity. Does he have enough of grid capacity to let that much electricity through, because there are also new communities coming up and maybe new industrial sites built up, and we have this uncertainty here. So we go back now a bit to the grid provider view, and we look at the unit commitment problem, which is a discrete time scheduling problem. So basically here, unit commitment problem is the main topic is just to ensure that the electricity production is equal to the electricity consumption in my grid. So it's basically a scheduling coordination problem, where you have to make sure that you match the energy demand and supply at minimum cost. And here you then basically try to optimize this by balancing all these players, where you then have, you can see in the picture, you can have industrial sites, you can have all these power plants, energy storage, and all of those, and you also have to take into account the power grid and its possible limitations. And then here you have to ensure, that's the big important factor, you have to ensure the most economical operations, because this will in the end reflect the electricity price that also affect everybody. And you also have to ensure that you, for instance, for the power plants, you follow healthy ramp up and ramp down phases and different kind of constraints that are ensuring a safe power distribution and generation. And it has to be also feasible towards the power grid's limitations. So here we see our steel plant can be in both a role of electricity producer and consumer. So let me go to the unit commitment problem. I stepwise, I show it stepwise the problem first, we have two indices. We have I for a generation unit and T for a time slot. Here you can see 5 time slots, so it's a discrete time problem. And at every time we have an electricity demand, PTD demand, which is shown by this curve. And then you have a variable electricity generation cost for each unit, I. And then your decision basically is to say, how much should each of my units generate at a certain point of time? So here you can then see these 5 generation units and how much they contribute to meet this objective main constraint that says the sum of generation should be equal to the demand at every time point. And here, the objective function would be to minimize the variable cost. But of course, it's more complex because the unit should also be able to turn off. So we don't only have continuous variables, we need binary variables. And we get these additional parameters when you look at the entire problem. So say, this is my generation unit, and typically it has a stable minimum and stable maximum generation point. So that means that if I have a power plant of 500 megawatt capacity, I cannot run it normally with 5 megawatts stably. So I have some min and max values. So say if I, for instance, want to say I want to schedule this unit to run here, it should be between a P max and P min. And then that means I also have to track if my unit is on, so the state of my generation unit. So then this n variable here would go on. That would be equal to 1 if my power unit is producing. And the same goes, I also have some startup and stop indicators. We have also some limitations and parameters, for instance, for minimum uptime and the ramp limits, as well as the minimum feasible generation that is shown here. So let me say I then want to ramp down. So I'm for the time point 2, I take this production down. And then if I do that, it's still on, but now I have to make sure that the difference between these 2 points is not bigger than my ramp down limit. And then I go down, maybe I take it down to the minimum level, after which I can shut it down, turn it off. And in that case, then the n variable, the binary variable goes to 0, but we have this start and shut down indicators, so the stop indicator goes to 1. And here, when I do this, I also have to make sure that my energy generation unit has been on enough of times. It has to meet the minimum uptime constraint, as well as if you then shut it down, it has to meet the minimum downtime constraint as well. And the objective function typically is here, you minimize variable cost of depending on the generation level, plus fixed cost having a unit on, plus then starting and stopping costs. So that would be, I will go very fast through this example here. You have this generation level constraint that says if it's on, it should be between P min and P max L0. Then you have ramp up and ramp down limitation constraints. You have some start and stop constraints that relate then n with the end start and then stop. And then you have this minimum up and down time constraint. This is one example of it. There are many examples how to formulate those. And then you basically are much more constrained that I don't have time to go through reserve. You have to account for some uncertainty in the demand and production and make sure that you have enough reserves in place. So you have variables and constraints for that. You also have network constraints, which you normally take care of in iteratively solving this MILP repeatedly. So this is going to be one of the key constraints in this talk. So if you look at the problem size, first of all, this is a fairly large problem. We have number of units is increasing with this energy revolution that is happening. Yesterday, we might have had 50 to 200 generation units. Today, we already talk about more than 1,000 plannable units that you have to plan in. And tomorrow, probably we'll have much more than 5,000 units. So that means if you take a planning horizon over 1 day, and you have one time grid is often 1 hour or maybe 30 minutes, even sometimes 15 minutes, you get then 24 time points, for instance, for 1 hour grid. And if you have a problem with 1,000 units, you get at least 24,000 binary variables for that. And plus, if you also consider the binary variables for starting and stopping, it even goes higher. So, you know, brute force method will fail. So we need to be able to even solve this unit commitment problem runs iteratively. Typically, we have to solve maybe 3 to 6, 7 runs within 5 to 10 minutes. So it's really important to get it fast. Optimization, again, plays a huge role here because we are often optimizing an entire country or a big state. So typically consumption could be 40 gigawatts. And if you take an average price of 40 euros per megawatt, which sounds like a dream today in today's world, this results in a daily generation cost about of 38 million euro. And annually we talk about 14 billion euro. So if you think about optimality, every % away from the optimal solution would mean a loss of 380,000 euro, which would be 140 million euro per day. And this is still acceptable. Typically use optimality criteria of 1%. But here optimization truly matters. So what we did here, we tried to speed it up using an LP heuristics, which is a very simple one. Basic target would be to try to speed up this solution of the UC MIP problem without losing on optimality. So there's a lot of literature about how you use rounding. So you solve the LP round values, but this doesn't work so well because it quite often results in infeasibilities. So the idea here was actually to analyze this LP solution and fix binary variables that actually respect the physical generation limit. So if you look at this constraint here, I highlighted earlier, if n is equal to 1, then you are between these limits. But if n is in the fractional, the LP solution could be fractional, then you basically your limits will be these ones here, which will be fully fine for the LP solution, but of course only above the P min it's feasible. So what we decided, we would analyze this constraint and we would try, what if the binary variable value in the relaxed solution times the predicted consumption here, what if that is higher than the P min? The idea is to say, if we satisfy this constraint, then it's fair to assume that if it's needed also in the relaxed solution, it would probably also be needed in the full MIP solution. So that means what we assume that it will be needed, we fix the variables to 1. And then basically what we do is we solve the LP for all these binary variables we analyze it, we check the constraint, if it's equal to, if it's true, we fix the variables, and then we solve the full MIP problem with partially fixed NIT variables. And this could be done in several passes. So now I will just show the results. This we tested with one example. There were 44 different instances of the same problem with 1,200 units. And you could see here basically that we got an average speed up of 3.7, which is quite good. But even more importantly here was that the largest solution time went from 131 to 12 seconds, which is almost the same as the minimum solution time for the MIP problems. And you can also see that the average solution improved. In average, we even got slightly tiny bit better solutions. And in this case, the worst solution was only 0.4% worse than the optimal MIP problem. So in this case, you can see that it really, this simple approach really helped the solution. We also tried a smaller example, which turned out to be much more tricky. So we only got an average speed up of 1.8, but you can see that we also increase the robustness. So we go down from almost 4 minutes to about 1 minute, the longest solution time. So that's one of the more important approaches here. But we could also see that here we actually didn't, in average, we got a slight worsening of the solution. And this one actually had 225 instances. So we had one outlier case that also had a significant worsening of the solution. But when we solved it in the iterative loop, we saw that they actually average it out. So it's not such bad a problem. So we can see many runs are better than MIP, and this comes from the fact that we use a MIP cap of 1%. So sometimes you can be lucky and get a slightly better solution. So it's a very simple approach. It can still make a big difference. And this is some kind of a solution, I would say, engineering-based solution, how to think about the problem. And as you can also see, there were very large variations on same instances. So really is how the instance comes up. It has a big difference on the performance. It's also possible to use this. You can build up, combine it with machine learning. We also tried that. Can we predict which binary variable should be always on? But it's also not so easy, and you have to have the right kind of specific data available for the training. So this proposed LP solution is relatively straightforward, also to do it in a productive environment. However, it also say in this relaxed solution, in our methods, we solve it twice. And in some problems, it actually took more than 50% of the total time. So if you could reduce, say, solve the LP, add the constraints and continue from that, basis, then that would also possibly speed up our algorithm. So with this, I would like to walk into the conclusions. What I would like to say here is I have been all the time trying to focus on this kind of electricity, how important it is to consider it both ways. And here we have talked a bit about the unit commitment problem as well as some industrial problems. So I hope I have been able to tell you that, convince you that electricity and energy is an important topic to be considering. And I hope also I have given you some insights to scheduling problems, also presented some approaches how to speed up large-scale optimization problems, and shared some of my personal experiences, and maybe also convinced at least some of you that MILP methods are a very good component in your solution system, but by far not sufficient to solve these large-scale problems. So it's always clear that what is maybe obvious to others isn't always obvious to us. So this is something, the conclusion is important. Optimization is critical to many industrial problems. And commercial MILP solvers also, they can also embed a lot of advanced algorithms outside the branch and cut itself with all the pre-processing and heuristics that they have built in. But MILP alone, even if you use these commercial solvers, they cannot do all the job for you. So you need some supporting heuristics. You need to use decomposition schemes. You need somehow support this kind of approaches. And apart from that, your model should be very tight and expandable. So this is one important topic that applies, of course, to any optimization problem. And then energy combines really these different players that don't know about each other's worlds. So demand-side management is one way of trying to seek and identify the flexibility in your process. And then in general, combining the scheduling of processes and scheduling of the energy is really hard, but it's necessary. If you look at the future scenarios, this is really necessary. So we really need to have more solutions that are crossing these domain borders. And here it's important that research cultures meet and collaborate. So mathematicians, computer scientists, OR people, together with different disciplines of engineers, and myself a chemical engineer, but also electrical engineers, software engineers are needed, as well as the people who really understand the physics and chemistry behind these different processes and phenomena. Of course, not to forget about industrial and academic collaboration. I have also spent quite a bit of time in my work to trying to bring academia and industry closer to each other and raise some new problems and interest on certain topics. And still, I have to say that there's still a lot of industrial challenges that could be optimized, but have not yet even been modeled, because partly the complexity and partly maybe the time and priority. So that would end my talk. I would like to maybe highlight, these are a few references that I have been talking about for those who are more interested. And with this, I would like to thank you, and I'm happy to take any questions.
Okay, thank you very much. So I allowed all the people here to unmute themselves, so don't hesitate to ask questions directly. And maybe I can start with one. So we have done also some work on energy optimization, and we have found that conditions and energy pricing models are quite different in every EU country, and they will evolve in the future, maybe in very near future. You are in a multinational company. How do you handle all of those differences?
The sound.
You don't hear me? Do you hear me? No.
Okay. Okay. Now I think I hear you again. I hope I hear you again.
Do you hear me?
Yes, now I hear you again. Sorry about that.
Okay, so I will just repeat my question. That the conditions and energy pricing models in different EU countries are different, and they will most likely change in the near future. How do you handle that? Because you cannot just develop one optimization system, but you need to have several ones to satisfy several countries. Do you see, for example, that there will be some EU norms that will unify these approaches so that it's a bit easier for us?
Yeah, I believe that I hope there will be some kind of EU norms. Of course, sometimes EU norms are maybe not so ideal for all the participant countries, so there will be probably some resistance and development needed. But one thing, you're completely right, the marketing landscapes are very different between different countries. And for instance, when you solve these kind of demand-side management problems, first of all, you see that how you connect, what kind of tariffs you have to take into account, what kind of penalty structures you have, and what kind of benefits you get. That's a huge difference. So this also, for instance, do you have 1 hour tracking, 30-minute tracking, 15-minute tracking, and so this is all different between countries. And also, when you look at the unit commitment problem, we are actually producing one of the leading software in this area, but a lot of the work, when you commission a unit commitment solution to a different country, a lot of work goes really into engineering and getting the specific requirements, business requirements from different environments settled. So this is a huge effort. Maybe the most important thing is, in my view, to be aware of potential differences and try to generalize your modeling approach or your system such that you can actually account for different approaches without changing everything. So that kind of to create an interface that allows you some flexibility. That would be the one that I also have tried to do.
On the problem complexity side, it's making a problem more difficult, because if you have more parameters and more variables, consequently, then it's much harder to solve, right? If you solve like more general problem. Yes,
that is true. The problem complexity, I would say, from my experience, and especially when you look at the demand side management problem, I actually thought about what should I present here, and there would be several of those I could show to you. But one commonality of each of them is that in some cases you are lucky and you can get one process working very well, or maybe even one type of process is working very well. But as soon as you change something in the process, or you change the process, nothing works. So it is still a very, very big challenge, because we are kind of all the time pushing the boundaries of where you can go with MILP, and there you have to use your imagination. What kind of methods do you then want to deploy to speed up and avoid some of those traps that you get into? Because of course, an industrial solution is not happy if it takes 2 hours to solve a scheduling problem that should schedule the next 24-hour production or something. So it has to go fast, and there's always this trade-off. So you have to kind of always have the healthy feeling of what is importance between the optimality and the performance, and with that try to reach that you actually can improve the performance, come closer to optimality, but you cannot only strive for this 0% gap in practical problems, else you can never implement anything.
Especially if nobody else knows better solution, then you are on the safe side, right?
Yes, that is also true. Yeah, that is also true. But because of that, it's also very important for let's say, people also to be aware of other developments and have an overview, and not only stay in your own chamber. And that, for instance, is also very excellent to have this kind of exchange, understanding different approaches. So I have also been quite often surprised on how elegant solutions there exist to solve a certain structure problems, but then unfortunately the problems I faced seldomly fit one-to-one in those structures.
Mm-hmm. Okay, so I would like to encourage other people to ask their questions as well. You can just simply unmute your mic, or you can type your question in chat. So if nobody does so, then let me a little bit ask with these smart networks and many things has to change, because the electricity will not flow only in one direction as before from classical producers to classical consumers, but also in the opposite direction. And and there will be much more active nodes, let's say active producers in a network. They are already today, right? So it requires a lot of changes on the, let's say, engineering side. Like a lot of equipment will be replaced, but from the optimization point of view, we probably can't handle it centrally. So there is probably some decentralized approach needed. As far as I know, in Czech Republic, they do kind of groups of those production resources that will be marketed together. For example, if there is like classical producers, they have just one group, but if there will be like small producers, they will probably be part of some consortia which will let's say run optimization algorithms for them to sell it at the best price, or to be maybe activated at certain moments when the price is good. So but definitely it's more distributed problem. So up to now we have handled these problems by, let's say, centralized solution. So what is your outlook to that? So what do you think that may change if it will be really distributed?
Yeah, this is a very good and challenging question. I mean, you have this kind of, especially many small solar and wind power plants are merging to become a bigger plant as well. That's very good to understand. But also there's these virtual power plants where basically also your battery storage is related. So you try to have, I would say, more stable units by forming something together. So that's I would say, a healthy development. And but in the end, I think what you need to do is, first of all, you have to have something that coordinates maybe an aggregated level. So it has maybe 50 or 100 units aggregated to one big unit. But then somebody, of course, has to coordinate the big game when it comes to grids. One of the keys there, if you have different industries, they have to also internally increase their optimization skills, because many industries are today scheduled manually. And if you use this kind of manual methods, it's almost close to impossible to kind of create the flexibility that you might need in this kind of demand side management, where you want to basically also act as a virtual power plant. You want to try to avoid big costs, and you want to also support the stability of the entire electricity system. So it's a challenge. I believe that maybe at least a simple solution could be even a control related solution that provides you some kind of short-term flexibility, where you have some buffers that you define that you then could aggregate to something bigger. And that could be something that would be there. But in the end, as I also showed with a picture of the sharks underwater and the houses on top of the water, we have two players and they have different responsibilities, and the industry has the true responsibility of being profitable and be able to produce good products. So they really need to analyze their processes. How much flexibility can they actually offer without risking their production quality? And that's what we also did with this early demand side management, the steel plant example. That was really one of the questions, and the conclusion was that yes, there is, in most processes, you have a possibility to do something, you have a possibility to get more flexible, but it requires maybe not optimization, but at least some kind of algorithmic support so that we can be very fast in reacting and automate part of this.
Okay, thank you for your answer. So is there any other question? I don't see it in the chat.
Can you hear me?
Yes, sure, go ahead.
Yeah, first of all, thank you for very informative talk. And I want to ask you if you considered, when you were optimizing like this steel casting factory, that you could exactly add the flexibility to the factory by, for example, building a battery storage for it. So like adding this into some global optimization of the production itself. Like if for the company it would be profitable to build this battery storage, and so you build a model which would optimize this problem and tell them then some managerial decision that it would in some time window it would be profitable to build such a thing and increase the flexibility by some investment?
Yeah, that's a very good question. I mean, in fact, a couple of steel plants I know, they even have some water power plants that they own. So in that way, they can also then try to, by themselves, use their own energy sources when needed to support this kind of high peak prices. For somebody like a steel plant, the consumption is so big, it can be about 200 megawatts per hour, or even more, 250, 300 megawatts per hour, the consumption. So also the battery storage type of volumes that they would need is a very huge thing. So, I mean, it's possible. It's also quite easy to embed in a model like this, what we have done. From the modeling point of view, it wouldn't be a huge challenge to add this kind of feature into it. But I think from the investment point of view, also looking at how successful and profitable the steel industry has been in the last decade, it's not that easy. But I'm sure that this kind of considerations for sure should be very, very carefully looked into, and maybe not even if not the steel plant itself invest to battery storage, they could maybe partner with another company, like also what Zenek is indicating, to form kind of a consortium where some people are actually having access and they can kind of have their internal partnerships and do that kind of possibilities. But of course, here legal things also come into place. If you have a market, liberalized markets, you have to be careful that you also follow the regulations of the area and country that you are operating in. But a very good comment. Thank you.
I see. Thank you for the answer.
Okay. So if it was the last question, so let me thank to Iiro for his talk. It was great to have you here. It was very practical and I think up-to-date topic. Energy is really every day on news today. And then let me remind you that there will be a next talk in 2 weeks. It will be given by Patrick Kasmaker from Leuven, and he will speak about data science, which meets scheduling community, right? So I will be happy to have you on board in 2 weeks. And once more, thanks to Iiro and his company for very, very informative talk. Thank you much and bye-bye.
Thank you very much also.
Bye-bye.
Bye-bye.
Bye.